Okay, so this is the test to go over the foundation electricity test. No, excuse me, the forces mid-topic test, and it's got some bits in from electricity, energy, matter, um, as well. So it's a bit of a mix. It's to kind of keep you sharp on everything, really. So I'll be flicking forwards and backwards between my responses and the mark scheme. So do add to your script information that you didn't get, cross out bits were wrong, bits that were wrong, and put in the corrections. So first one, these pictures show 4 objects. Each object has had its shape changed. We got a metal ruler, bungee cords, springs on a playground ride, molded plastic car body. Which of them are storing elastic potential energy? I've gone for B and C. Explain the reasons for your choice or choices. So both the bungee cords and springs have been compressed in an elastic way and are able to return to their original positions. A has been plastically deformed, which is this bit here, plastically deformed. So the energy used to change its shape can no longer be released as kinetic energy. So let's see how many points I would get out of 3. And I've got the wrong mark scheme here, so just bear with me. So that's a bit better. So I get 1 mark for B, which is good. I get 1 mark for C, which is good. And I get 1 mark for saying that they will go back to their original shape or size. Okay, so I've hit all of those marks, so that makes me very happy, and I crack on. So the next one, part B. A student makes a simple spring balance. To make a scale, the student uses a range of weights. Each weight is put onto the spring and the position of the pointer marked. The graph shows how increasing the weight made the pointer move further. So at the moment there's 2 weights on and the pointer's at 8. This is the graph of the results it gives me. Which is the unit of weights? You should say Newton. That's right. And I have said the range of weights. Well, you can see that the first here, the first point was in 1 Newton, at 1 Newton, and the last one was at 5. So I said from 1 to 5. Let's just have a quick look at the answers. So newtons would get me a mark. 0 to 5 or 5, except 1 to 5, yeah. So that would get me the marks. You can adjust yours as necessary. So it's cracking on. How far does the pointer move when 4 units of weight are on the spring? So I've gone for 16, and what I did is I went up with a ruler to the line, and then across with a ruler, and then I circled. Mouse has gone a bit funny there. I circled the read off, which, let's see if I can zoom in a bit so you can see it, which was 1 small square above 15, which gave me 16. So I've gone for 16 centimeters. Student ties a stone to the spring stretches 10 centimeters. What's the weight of the stone? So you had to do the same technique in the opposite direction. So with a ruler, starting from 10 centimeters, go across the line and go down vertically with a ruler, and I got 2.4 newtons. So let's check the answers and see how I did. So 16 centimeters is fine. I'll get the marks for that. The answer is 2.5, and so luckily I was in the acceptable range between 2.4 and 2.6. So give yourself those marks if you deserve them, if you've got them. So yeah, the key thing is about doing read-offs and things that you need to be very slow and careful with your ruler use. So you have to go across horizontally with a ruler and down vertically, and try not to get your ruler anything other than purely horizontal or purely vertical. Alright, if you're too sloppy, you will probably end up losing marks somewhere. Question 2. The diagram shows an adult and a child pushing a loaded shopping trolley. So the mum provides 40 newtons of force forward. The son, it looks like, provides 10 newtons forwards. What's the total force? 10 add 40 equals 50 newtons. So would I get that? Yes, I would. So 1 mark for that. Which one of the terms in the box means the same as total force? I've gone for resultant force, and that is the answer. Resultant force down here, so 1 mark for that. Remember, resultant force is the overall force that takes effect once you have added up all of the forces, remembering to take into account their directions. So it's a really important concept in forces, the resultant force. Part 3, the trolley is pushed at a constant speed for 80 meters. Calculate the work done to push the trolley 80 meters. Show clearly how you work out your answer. So you always start off putting down the formula that you use. So work is equal to force times distance moved in the direction of the force, or W equals F times D. Force was 50 newtons, the distance was 80 meters, so that gave me 4,000. And notice that there's no units there, so they probably have a mark for adding them in. And there's two acceptable units for work, either joules or newton meters, capital N, little m. Let's see how I got on. So 4,000 for 2 marks and joules for 1 mark. So I also give you permission to give yourself the marks if you put newton meters, because they are acceptable. They are acceptable units for work. Okay. So bit of a ambiguous questioning, you know. Not super straightforward is the next one. Part 2. B. Drawing a ring around the correct words to complete the sentences. The unit of work done is the joule. Most of the work done to push the trolley is transformed into. Now, it's not light, because trolleys don't create light when they're being pushed. They do create a bit of sound, and the friction between the wheels and the ground, and also the metal of the trolley moving through the air would create heat or heating, which would represent energy being dissipated into the thermal store of the environment. So it was a bit of it was either heat or sound. Now the thing about sound is, when the energy in sound spreads out in all directions when it comes from the source, in this case it would be a trolley rattling, sound is simply the vibration of particles. And so when those vibrations would die out, all that energy would simply go into the thermal store of the environment. So actually sound was an intermediate transfer and not the end of the energy transfer process. So heat is the correct answer. Give yourself a mark if you got that. Question 3. A powerlifter lifts 180 kilograms lifts a 180 kilogram bar from the floor to above his head. There's a picture. Use the equation in the box to calculate the weight of the bar. Show clearly how you work out your answer. Use gravitational field strength as being 10 newtons per kilogram. So it's always the mass times the gravitational field strength. So I put down my formula, W equals m times g. Remember, g is the gravitational field strength, or the acceleration due to gravity. There's two ways of saying g. So Then I've substituted my numbers in, so I've got a mass of 180 kilograms and a gravitational field strength of 10, which gives me 1,800 newtons. Part B, the powerlifter uses a constant force to lift the bar a distance of 2.1 meters. Use the equation in the box to calculate the work done by the powerlifter. Work is force applied times distance moved in the direction of the force. Show clearly how you work out your answer and give the unit. Choose from the unit from the correct list below. So work, we've already said the correct unit is the joule. Again, starting off with an equation, work is equal to force times distance moved in the direction of the force. Put in my numbers, get an answer, and don't forget to put the unit. So 1,800 gave me 2 marks for the one before. So 1 mark for putting the numbers in the right place, even if you somehow got the numbers wrong. Part B. Was that the one we were doing? Yes. So 1,800 times 2.1 gave you 3,780. Did I get that? I did, and the unit was the joule. So 3,780 for 2 marks and 1 mark for the unit joule. At the end of the lift, part C, the powerlifter holds the bar stationary above his head for 2 seconds. How much work does the powerlifter do on the bar during these 2 seconds? Draw a ring around your answer. So it was a trick question. If you don't move and your bar is stationary, the bar is not going upwards or downwards. The distance moved is 0 and work is force times distance. So if you times any number by 0, you get 0. So my answer was 0, no distance moved. Let's check the answers. 0. Work is only done when a force makes an object move. Except distance move is 0. Except no energy transfer. Except the bar is not moving, is stationary. Fine. Cracking on. So 6 marker. Just to mention about question 4 and 6 markers nowadays. So the quality of written communication isn't quite as strict as it used to be. So you should always try and communicate your science so that the examiner understands what you're talking about, but you won't be explicitly penalised as much as you were in the previous GCSE specifications if there are slight problems. The information in the box is about the properties of solids and gases. Solids, they have a fixed shape, are difficult to compress to squash. Gases will spread out and fill the entire container. Gases are easy to compress, squash. Use your knowledge of kinetic theory to explain the information in the box. You should consider spacing between particles, movement of individual particles, the forces between particles. So, kinetic theory, and this is the start, is really just another way of saying the particle model. Alright? So you've got to use the particle model to explain the properties of solids and the properties of gases in the box. And you should be talking about the 3 bullet points that they've asked you to. Right, so my response, and I wasn't completely happy with this actually. Solids have a fixed shape because the particles are touching and are in fixed rows. In contrast, so I recommend that you use the phrase in contrast to show something's different. In contrast, gases take the shape of the container because particles are not touching each other and are moving quickly in random directions. In solids, particles are close together and have larger forces between them. In gases, particles are separated more and have weaker forces between them. Solids are incompressible because the vibrating particles are touching, whereas gases are compressible because there are large amounts of space between the particles. So, let's see how I would have done. So, so to get 1 or 2 marks, I need to have considered either a solid or a gas and describe at least one aspect of the particle. So I think I've done that. So I'm beyond that descriptor. For 3 or 4 marks, have I considered both solids and gases and described aspects of the particles? So I've done that. So I reckon I'm probably on the 5 to 6. So I'm either going to get 5 or 6 marks. Consider both states of matter and describes the spacing and movement forces between the particles. Explains a property of both solids and gases. So I did say that solids are touching. I didn't make it clear that there was no way of particles to move closer, so I think I could have done better there. I did say that they vibrate. I could have improved by saying around a fixed point. Strong forces of attraction, so I did say that for solids. The forces became repulsive if particles get closer. I didn't say that. Okay, and that is the point. If particles become too close, forces do become repulsive. That's a really high level point actually. There's quite a lot more science there. Particles are strongly held together, not free to move around. I did say that. Gases are far apart. I said that. There's space between particles. I said that. They move randomly. I said that. There are negligible or no forces of attraction. So negligible means that something is so small it can be ignored. It's a good science word. So I said weaker force of attraction, so I'll probably be able to tick that one off. And did I say they spread out in all directions? I didn't use those words, but I think I mentioned it in a part. But I'm getting 5 or 6 out of that. So yeah, mark yourself and give yourself what you feel that what the mark scheme says that you're able to get, and do take the time. And let me just zoom in a little bit on this for you. So here it is. Pause the video if you need to, and add in onto your scripts the things that you missed. So let's carry on. If you didn't pause, and if you did pause, well done. Let's continue. Question 5a. The diagram shows the circuit used to investigate the resistance of a sample of material. The diagram is not complete. The ammeter and the voltmeter are missing. Part 1. Draw the symbols for the ammeter and the voltmeter in the correct places. So you needed to put the ammeter in the series part of the circuit. So here would be fine, or here would be fine, or here would be fine. The voltmeter needed to go in parallel, so across the material. Okay, so there will be 1 mark for each of those. I'll just confirm that. So yeah, 1 mark for an ammeter symbol with an uppercase A in it, 1 mark for the voltmeter one if it is in parallel with a capital V across the material. Next one. How can the current go through the material be changed? So I've said after the resistance, alter the resistance of the variable resistor. So the mark scheme says adjust or use the variable resistor, or change the number of cells. So yeah, you can add that alternative response in as well. That would have also been correct. Next one. Material called conducting putty is rolled in cylinders of different lengths but equal thicknesses. Graph 1 shows how the resistance changes with length. The current through a 25 centimeter length of conducting putty was 0.15 amps. Use graph 1 to find the resistance of a 25 centimeter length of conducting putty. So the technique here is you had to get your ruler and you had to extend the straight line upwards to 25. And you had to use your ruler, go upwards to the point where your 25 centimeter line intersects with the line of best fit, then go horizontally across and read off. So I've made it 38 ohms. They say 37.5, but I'm within the tolerance. I'm between 36 and 39. So give yourself the marks if you've deserved it, if you've met that criteria. Next one. Use your answer to B part 1 to calculate the potential difference across a 25 centimeter length of conducting putty. Show clearly how you worked out your answer. So, voltage is current times resistance. And You can only use this relationship known as Ohm's law if temperature is constant. So actually it doesn't say anything about that. So maybe that will be relevant to a later part of the test. That's just popped into my head. So current is 0.15 amps. It gives it to you up here. And 38, that was what I got from my read off, 38 ohms. So I've got an answer when I multiply 0.15 by 38 as 5.7 volts. So 5.625, or their answer to B part 1 times 0.15. So I'd get that. Alright. So let's carry on. A second set of data was obtained using thicker pieces of conducting putty. Both sets of results are shown in graph number 2. So this is the thicker results added onto a graph with the thinner ones already plotted on. What is the relationship between the resistance and thickness of the conducting putty? So I think I have answered the wrong question, so I'm expecting to lose marks here. The gradient of the line is shallower, and that would mean it has a lower it means it has it offers a lesser resistance. The thicker one offers thicker cylinder offers a lesser resistance than the thinner one. So the thicker the piece of conducting putty is, the lower resistance is. So the answer I think I'm looking for is as the thickness goes up, the resistance goes down, which is not a directly proportional relationship as I had. It would be an indirectly proportional relationship. So I think I've rushed that question and got it wrong. Let's have a look. The thicker the putty, the lower the resistance. So yes, I understood it. I would have got it right the second time, but I would get 0 marks. The thicker the putty, the lower resistance. Next one. Name one error that may have reduced the accuracy of the results. Thicker line of best fit does not represent the spread of data. Let's have a look. So measuring the length incorrectly. Okay, if the person did that, it would lead to less accurate results. Measuring the current incorrectly. Okay, good. Measuring the voltage incorrectly. Not calibrating the ammeter of the voltage. The thickness of putty is not uniform. The meter had 0 error. So except as a source of error, the temperature of the putty may have changed. So actually my response isn't on that list, and so I wouldn't get a mark, which is a shame really. So add in those responses onto your script. I would say that ones to remember going forwards are calibrating the voltmeter and ammeter, or connecting them incorrectly into the circuit, or if the material had a temperature which changed. And as I mentioned earlier, if the temperature changes, it means that you can't use Ohm's law. Alright, so that's a shame I wouldn't get that one. Where am I going? I'm going over here. In the motor, the electrical energy is transferred into other types of energy. Some of this energy is useful and the rest is wasted. Name the useful energy output of an electric motor. I said kinetic energy. Our mark scheme says kinetic energy. Okay, you could say gravitational potential energy, or GPE, because the motor is moving the weights to a higher height, which is increasing the GPE store. Next one. What eventually happens to the wasted energy? I said dissipate into the thermal store of the environment. they have said dissipated into the surroundings. So just like to draw your attention to this word dissipate, really. So if energy is dissipated, it means it's spread out into the thermal store of the environment into a way that you can never get that energy back. And a physicist would say that transfer is irreversible. So please try to use this phrase, energy being dissipated into the environment. So if you rub your hands together, you're transferring biological energy of your muscle, or maybe chemical energy in your muscles, to the thermal store of your hands. But as your hands cool down, that energy is dissipated into the environment. So just another example of how we can use the word dissipation in physics. Okie dokie. Another graph question. What can you conclude from the graph about the relationship between the load lifted and the input energy needed? So I can see it's a 2-mark question, so I need to give 2 responses. So I'm structuring my response using bullet points. As the load increases, so does the input energy. Okay. Higher loads require much larger amounts of input energy to lift. I said more than 5 newtons as compared to smaller loads. So let's have a look. Energy increases with load. So 1 mark for my first point. So further amplification, which fancy way of saying further detail, increases slowly at first, then increases rapidly. So that's what I've said. I haven't quite used those words, but I'd get credit for that. So a shop uses escalators to lift customers to different floor levels. The escalators use electric motors. When the shop is not busy, some of the escalators, are turned off. The sign tells the customers that escalators are turned off to save energy. Each escalator has 1 motor with an average power of 4,000 watts. The motor is turned on for an average of 8 hours a day, 6 days a week. Electricity costs 15 pence per kilowatt hour. Calculate the cost of electricity used in an average working week to run 1 escalator. So just to put your mind at ease, really, so you will not on the new course have seen this larger unit for energy. So a kilowatt hour is when you times a power in kilowatts by a time in hours, and it's a much larger unit of energy than joules. And we use kilowatt hours to bill customers for the electricity that they buy. So 1 unit means 1 kilowatt hour of electricity, and in this company, this electricity company, are charging whoever owns the shop 15 pence per kilowatt hour that the escalator uses. So the cost of electricity is over a week to run this escalator. So power is energy divided by time. So that's this bit here. So rearranging it for energy, you get energy is power times time. So the easiest way to do it is convert the 4,000 watts into kilowatts. And to go from watts to kilowatts, you need to divide by 1,000. So there are 4 lots of 1,000 in 4,000. So I've got 4 kilowatts here. And then I have to work out the total number of hours that the escalator was used in the week. So that's 8 times 6. So 8 hours a day, 6 days a week. So I end up getting 4 times 48, which means I use 192 kilowatt hours of energy in that week. I then times 192 by 15 here to get my total amount of pence, and I got 2,880 pence. And in my head I thought, well, how much money is that? Well, that's £28.80. So that's kind of a sensible amount for 1 escalator to cost during a week. You know, if it was like 1p, I think that would be a silly answer because it would be too small. If it was like 1 million quid, well, that would be far too big. So I just did a little conversion in my head to see if my answer was sensible. So that's increased my confidence, but let's see if I was right or not. So energy is equal to power times time. 2,880 was the answer. So I get all 3 marks for that. if you messed up and you got your decimal point in the wrong way because you forgot to change watts into kilowatts, you would get 2,880. If you manage to convert, if you manage to find out that 48 hours were used on the typical week, or you did the kilowatt conversion, so you managed to change 4,000 watts into a kilowatt, into 4 kilowatts, you would get 1 mark. If you had made the correct substitutions or put the numbers in the right places, having written down the formula, you can get a maximum of 2 marks for that. So just to put your mind at rest, they will not ask you about kilowatt hour ones in the spec. Part 2. Give one environmental advantage to turning off electrical appliances when they're not being used. Well, I said to save energy, less CO2 produced by the electricity company. So let's see. It was only a 1 marker, so I decided to go shorter. So actually, if I just left it as saves energy, I wouldn't have got the mark. But because I have gone a bit deeper and I've said that there's less CO2, which is a pollutant gas released into the atmosphere, I would get the marks. So I've just decided to be a bit safer there. So I just decided to expand on my initial response, and I've been rewarded for that. Okay. So here's a chest expander, 3 springs. A person pulls outwards on the handles and does work to stretch the springs. Complete the following sentence. When the springs are stretched, I said elastic potential energy is stored in the springs. The answer to that was here, elastic potential. So I'd get the marks for that. Figure 2 shows how the extension of a single spring from the chest expander depends on the force acting on the spring. How can you tell from figure 2 that the limit of proportionality of the spring has not been exceeded? So I said that there is still a linear relationship, which means there is just one straight line. The graph hasn't yet reached a force at which it starts to flatten. So let's see. The line is straight. Fine, I'll get the marks for that. So, excuse me, let's crack on. So, next one, use the data from figure 2 to calculate the spring constant of the spring and give the unit. Okay. So, this is something which is worth just taking a bit slower. So, do you see that extension is on the y-axis and the force is on the x-axis? Okay. So, the relationship between force and extension is Hooke's law, which is F is equal to the spring constant times x, which is the extension. And remember, K is the spring or force constants, 2 ways of saying the same thing. So if force was on my y-axis and extension on my x-axis, the gradient of the line would be the spring constant. However, do you see that it's actually the other way around? The extension is on the y-axis and the force is on the x-axis. So what this means is my spring constant, my K, is actually the inverse of my gradient. And by inverse, what I mean is this bit here. So 1 divided by my gradient is equal to the spring constant. So gradient is always change in y over change in x. So on my y-axis, it's the y-axis reading finished at 0.4 and it started at 0. So that's my change in y-axis down here. My change in x-axis was the line finished at 160 newtons and it started at 0. So 160 minus 0. So I did that on my calculator and it gave me 2.5 times 10 to the minus 3. And I know that's a really small number and I didn't panic. what I then did is I did the inverse of it. So in my calculator, and it refers to this bit here, I did 1 divided by that number, which is how you do the inverse. And that gave me 400. The units of spring constants, and I checked the graph. The force was in newtons, which is fairly standard, and the extension is in meters. So my unit of spring constants would be newtons per meter, and another way of writing that is newtons. So capital N, little m to the minus 1. So let's see how I got on with the mark scheme. So 400 newtons per meter, so that gets you credit. Okay. So I have missed out the last page in the test, which is a disaster, really, isn't it? Because I would lose the 5 marks that are available. So that is a complete disaster. So don't be like me and make sure that you finish the test. I'm going to put the mark scheme up for the last ones. That's the mark scheme for the last ones, so that you can mark yourself. So you can press pause if you need to. That's a typical thing you find in exams, is maybe not checking the back page and seeing that there's any writing on it. So I missed that, and I'd be punished for that. Okay, so I hope you find this video helpful.